Okay, so back here looking at ionic compounds, remember they form lattice structures, which are crystalline structures, which are repeating patterns of the same unit. They're called formula units. In this particular case, this one looks like it's sodium chloride, which would be a 1-to-1 ratio, so it repeats and it forms this like cuboidal type pattern in the lattice structure. Now, not all of them form that exact same shape, but it is a repeating pattern that forms different shapes, and the lattice structures are built based off of the alternating positive and negative charges. Now, these are super strong. Remember the melting points on the ionic compounds. You did the little tray activity and the rock salt did not melt. Has to be super high. Those positive, negative attractive forces, they're called electrostatic or coulombic attractions. They are very, very, very strong, so would not break apart very easily. Now we're going to be looking at molecules. So, starting off here, we need to know why this occurs. It's called the VSEPR theory, valence shell electron pair repulsion theory. And basically what's happening here is you have lone pairs and bonded pairs of electrons around a central atom. Here's your central atom. Here's a lone pair, and then of course these are all bonded atoms here. And they have bonded electrons sharing a pair of electrons. Those are all single bonds. Now what happens is they repel each other. Because electrons are all negatively charged, they repel one another and cause them to spread out, try to get as far away from one another as they can. That creates certain geometric patterns in our very small molecules. Okay? So keep in mind, we're looking at, yes, how they have to spread out. Now, one thing to acknowledge is the lone pairs do take up more space. So when they have lone pairs, that creates different shapes versus molecules that do not have lone pairs on the central atom. So allows us to predict this VSEPR theory, the shapes of the small molecules, and we have to draw them, some of them in a three-dimensional view because they are not flat and in a plane. So what we're going to do, or I'm going to do the best I can. I am artistically challenged, so I will warn you up front. In a plane, you're just going to draw a line, then you do the wedge for things that are supposed to be coming forward at you. So draw the wedge, like so. And then the dashed line is for things that are behind the 3D part. Okay, like so. We're going to be using those configurations in order to draw the 3D ones a little bit better. So now we're going to talk about these different types of molecules. And their generalized formula is over in the left-hand column here, like AB. AB is a type of molecule where you have just two atoms, basically. Two separate atoms bonded together really is only going to create a linear molecule. So you have a point A to point B, and it just forms a straight line. So I'm going to pass around the models as I build them too, so you can see them, in a plastic ball and stick model. We call these ball and stick models rather than Lewis style structures. But the one I'm passing around where they're identical atoms, like fluorine, F2. Well, that's going to be linear. It's got two atoms. This one's more like HCl, where you have the chlorine and then you have the hydrogen. Okay, so they're different, but still in a linear line. Okay. So for ball and stick model for that one, if we're drawing HCl, the Cl, of course, would be a bigger atom connected to the hydrogen, which would be smaller, straight line. So anything with just two atoms is always going to be linear, period, end of story. However, there are other ones that can also be linear. It's an AB2 arrangement. It means it has two ligands attached to the central atom. And carbon dioxide is one of these examples. Okay. As you can see, you remember drawing carbon dioxide, it has two double bonds, but it creates a linear shape. Here's carbon in the middle, the black one, and the two red ones are the oxygens. But pass it around, this one's going to form a linear shape. So I'm going to draw this one for you too. This is another one that looks, but when you draw these ones, make sure you do add two bonds to make it show that it has a double bond in it. Like so. Okay? Now, couple other added clues. What you're looking at here, in the case of one that has 3 atoms, like the AB2 one or carbon dioxide one, looking at the central atom, this is where we care about lone pairs. Are there any lone pairs on the central atom? That would be a no here. No lone pairs, but it has 2 atoms attached. That's how I like to think of it. No lone pairs, 2 atoms attached, it's automatically going to be linear. Now, just another added little hint here. When you have this arrangement, usually ones that are going to create, be attached to 2 atoms and have no lone pairs, one thing you're going to see a lot of in this arrangement is double and triple bonds. Because in order for them to have no lone pairs, they've got to have everything bonded up. The other thing that you'll see on these particular ones is usually in the center, it's going to be a carbon group central atom. So keep that in mind. Carbon group central atom. Carbon group, what's 14 or 4A? Central atom. I put Ca for central atom. So if you see a carbon or a silicon or a germanium in the center, because we're sticking with the nonmetals and metalloids here, and it has 2 things attached to them, it's most likely there's not going to be any lone pairs, and it's going to be a linear shape. Okay? And the 3D diagram, we're going to be drawing ball and stick models instead of structural formulas, because basically the Lewis dot structures that we draw are structural in nature. So we're going to be sticking with ball and stick along with drawing the Lewis dot structures on the practice problems later on. Now, looking at another arrangement, this is also an AB2 here. AB2, right? That one, except for the main difference is on the central atom, yes, we are going to have lone pairs. You can have probably 2 or 1 lone pair. Most of them you'll see that arrangement. 2 or 1 lone pair. That's going to give you the bent shape. The bent shape molecule like water. So let me draw water here. Using red, of course, to represent the oxygen. And then we have our hydrogens there. The bent-shaped ones, because on the oxygen there's lone pairs, it pushes the other 2 atoms towards each other. Like I said, those lone pairs like to take up more space. So it narrows the angle between the 2 hydrogens. So here's an example of water in a bent-shaped molecule. You can pass that one around. And if you're big on angles, and angles helps you remember shapes, you're welcome to remember them, although you don't really have to know the angles until AP, okay? But obviously linear, what's the angle on this? That's pretty easy. 180, straight line, right? So the angle here is a little bit different. It's 104.5. Once again, you don't have to know it, but if you're good with numbers and this is how you remember things, I'm going to let you decide if you need to, if that will help you remember the shapes, okay? And when you also were looking at the PhET simulation, you saw the lone pairs, and they kind of have them as like clouds, like Mickey Mouse ears up here, like that. Okay, if that helps you to draw them in, to help you remember that's going to be bent, the lone pairs push the other 2 atoms down. Okay, you're welcome to do that. So the little green with the dots are my version of the lone pairs on the simulation. Now, for the trigonal or trigonal planar, depending on how you'd like to say it, doesn't really matter. And when you're writing this out, you can just put T planar. You don't need to keep writing out that word, because really that word is just telling us it's got some kind of triangular pattern in it. Okay? And it has 3 things attached, the tri part. We're looking for 3 atoms here. Okay? This particular one has to do with boron. Remember, boron does not like to have 8 electrons. It only does 6. It is different. It is an exception to the octet rule in that respect. Boron, if it's in the center, is going to form the trigonal planar shape. The other ones are ones that are going to have double bonds on them. So let me show you one with a double bond on them to make the flat triangle. Here, as you can see in the plane, the triangle is right here, but it is in a single plane and it is flat. So this is that's why it's called planar, because it actually is a flat triangle. Okay, so you can pass that one around. So I'm going to draw both of these examples for you so you can remember that, of course, boron single bonded because it does 6 electrons. So if we're talking about boron here, it's going to bond to, could be hydrogens or it could be halogens. Okay, and as you can see, the angle spread on this, if a circle is 360, the angle is going to be 120 degrees. But if you're drawing something like sulfur trioxide SO3, the only other main difference here would be that you have sulfur in the middle, and you would have the one oxygen, the other oxygen, and one of the oxygens has the double bond on it. And you drew that one in the Lewis dot structure examples, but one of the oxygen has a double bond on it. But as you can see, they still form, once again, this 120-degree angle, spreading out as far away from each other as possible. Next example, another AB3, except for the differences on these ones, the central atom has lone pairs. So, once again, distinguishing, does it have lone pairs, does it not have lone pairs? Has lone pairs is going to be pyramidal. The lone pair on, usually it's one lone pair, and on the top it pushes the other 3 down, so it makes this mini pyramid shape. And in our plastic models, we use the pink ones for lone pairs. So as you can see, it looks like a little mini pyramid. It pushes the other 3 downward, and it's 3-dimensional, so we have to use our wedges and dashes now. Okay. So as you can see, looking at that, and I'll give you a little hint, usually these guys that are pyramidal are, the central atoms are from the nitrogen group. So, usually nitrogen group central atoms, this nitrogen group is 15 or 5A, and those are the central atoms on these ones usually. And now we have to draw our wedgies. So it's supposed to come forward. The dashes make it go backwards. Although my dashes never look really good on the smart board. But it's supposed to be a mini pyramid. And don't forget, yes, there is this lone pair sitting on the top, pushing the other 3 downward, creating that mini pyramid. NH3 is a good example. PCl3, as you see the examples here, the central atoms are usually from the nitrogen group. And last but not least here on this particular, these are the normal regular shapes, not the expanded shapes. We're going to get into a few of those. Very easy one to remember because the generalized formula is AB4. So 4 things attached to the central atom. What's the prefix for 4? Tetra, right? So this one's a pretty easy one to figure out and remember. What you will realize is these guys do not have lone pairs on their central atom. And what you're going to find too on these guys, most of the time they're going to be carbon group central atoms. So 14 or 4A central atoms here. 4 things attached. If you look over here, C and C, you could have Si, F4, other things like that. 4 things attached, no lone pairs. Once again, you would draw this one with the 3-dimensional wedge and dashes. Let me pass around the classic model. This one flips and turns, is very symmetrical, like CH4, CCl3, okay? But it is 3-dimensional in nature. So here we have carbon, and I guess I'm going to attach some chlorines here. And here comes the terrible dashes. Let's see if I can do it. Not very well, but whatever. You get what I'm trying to do here. Dashes don't come out very well on the smartboard, but it's basically the same thing as pyramidal, but instead of the lone pair on the top, you have a bonded atom on the top. Any questions so far? All right. Oh, angles, if anybody's big on angles, this angle right here is about 107. and the angle on here is 109.5. If you're visualizing with the angles, just so you know. As you can see, pushing it closer together, the angles get less when you have lone pairs. Okay? Just a couple more, looking at the expanded octets real quick. Expanded octets, remember, are ones that have more than 8 valence electrons. You looked at this in that simulation. They're the third period and below. They can deviate from the octet rule. And some of them utilize the d orbitals to make space for the extra electrons. Sulfur, phosphorus, silicon, and chlorine are common examples that form expanded octets, just so you know. So looking here, the bipyramidal, which is AB5. AB5 is the generalized structure, no lone pairs on the central atom. And the previous slide also told you which ones typically are going to be in the center. But the bipyramidal shape has 5 things attached. There's usually the one plane that goes up and down, and then you have like a triangle that rotates around the center. Okay? So it looks like a pyramid on this side, and then you flip it, and then you have the other pyramid on that side, so that's why it's called bipyramidal. It's basically 2 pyramids stuck together. So we pass that one around. I'm going to do my best to draw it, so let's have fun here. Actually, I'll make the central atom a different color. And the ligands, they can all be the same. Okay, so we have our one plane, the up and down straight linear part. Then, basically, it forms kind of like a triangle. And then I can't do the dashes very well, but. So, there's a couple different angles here. When you can't really see the rest of the atom, but so I'll draw that there. These angles from here to here are 90 degrees. That didn't look very good, so let's redraw that. The angle from the top to the bottom across the linear would be 180, and then the ones in the middle between the triangle part, of course, those are 120 degree angles. Okay, so there's a couple different angles in here. You got some 90, you got some 120, and you have 180. Examples, see the P's here. They have 5 things attached. Very easy to see. And then, of course, there's 10 valence electrons being shared on that central atom. 5 things attached means there's 10 electrons being shared around the central atom. Now, AB6, which is the last one that you're going to learn in honors, AP does about 4 more shapes. There's the T shape, the seesaw. If you went through the FET, you would have seen some of the other ones. You're not responsible for knowing those this year. But if you do decide, to jump up to AP, you would have to know all of them. But the octahedral is not a hard one to know either because it always has a central atom with 6 things attached. No lone pairs. No lone pairs on the central atom. Octahedral, I think it's because when it forms its shape, it really has like 8 sides to it. So the octahedral is very similar to bipyramidal except for 4 things around, or it was 3 things around the equatorial, the middle section. Now you've got 4, so it kind of looks like a square around the middle section. Okay, so pass that around for your octahedral. Do my best to draw it too. Go with central atom. I'll use different ones for the lines. That way it'll won't mess up. Try to do the dashes. Okay, the dashes don't come out, but anyhow. So we have blue, blue. And then you have a bunch of 90-degree angles. This basically forms a bunch of 90-degree angles along all of its planes. Any questions so far? So now we're going to do some practice. We're going to draw the Lewis dot structures. We're going to look at the central atom, how many things are bonded, how many lone pairs, to decide on the shape. All good? Any questions? All right, for the polyatomics, remember the key is still count out the valence electrons of your atom. So sulfur has 6. Oxygen is 4 times 6, so that's 24. But the -2 also brings in 2, because as a group it latches on to 2 electrons, so now it has 2 extra. So that is a total of 32, right? Okay. But now you just follow the same pattern of assigning central atom sulfur, attach the ligands, which are the oxygens. Okay, I've used 8 of my 32, now I'm down to 24. And then I satisfy the octets of my ligands. 2, 4, 6, obviously there's 4 of them, so 24 electrons will go, and we're down to 0. The only thing that's added extra on the polyatomics is you need brackets and the charge outside designating that it is an ion. Now, what I also want to point out to you on the polyatomics is polyatomics are really involved, they involve both types of bonding because it acts as an ion since it has the -2 and the extra 2 electrons. But within its group, right here, these bonds from the sulfur to the oxygens, those are all covalent bonds. They are sharing electrons there. So it has sharing and it forms an ion. So there's sharing bonds that are covalent, but then it acts as an ion and does ionic bonding. So there's both types of bonding involved in this structure here. Okay? Now, the ball and stick model, 4 things attached, no lone pairs. What are we going for? 4 things attached to the central atom, no lone pairs means it's going to be what shape? Tetrahedral. So we know that. Tetrahedral. And then, of course, when you draw it, ball and stick model, you got to use the 3D that you can. Do the best that you can with your wedge and stuff. And the dashes to try and make it look 3D. There you go, ball and stick model. So that one, of course, is sulfate. Let's look at carbonate. Carbonate, when you draw it, let's go ahead and calculate it. Carbon brings in how many valence electrons? 4. The oxygens, 3 times what? 6, that's 18, good. 6 valence electrons for each oxygen. The -2 gives us 2 more, so we add that in. So we have a total of 24 electrons to work with. Who's going to go in the center? Carbon. Attach the oxygens as ligands. Very good, like so. How many did I use? 6. I'm down to 18. Now I'm going to satisfy the octets of the oxygen before I try to worry about the central atom. But I'm going to end up running out because I'm going to use up all 18. I put 18. 6 per oxygen. So this one's going to need a what? Double bond. Doesn't matter which one you take it from. Okay, create the double bond. Don't forget your brackets. Don't forget the charge outside. However, it doesn't really matter which double bond I put it on because it's going to equally distribute to all 3 oxygens. So this structure also has what? Resonance. Very good. So make sure that you would star it, and say, of course, resonance. Okay, as it states here. Make sure that you do that. Now, for shape. 3 things attached. No lone pairs on the central atom. What shape are we talking about here? The trigonal planar. Okay, so when you draw it, make sure that you have one of the oxygen double bonded, and make sure it looks like a flat triangle. And you can just write T-planar And there you have it. Okay, any questions? So that's how you deal with polyatomics. Now, if the only polyatomic that happens to be positively charged is which one? Ammonium. And that +1 means you do what to the electrons? You need to subtract one from your total because it lost an electron in order to, or it ended up having a net charge of 1 positive, so the hydrogen coming in didn't bring its electron with it. So when on ammonium, you just take 1 away, okay? So I know that's in the homework. Make sure that, you do the snow day. If we have a snow or a winter day, make sure you do the homework too.